Looking at section 2.3, polynomial functions and their graphs. We are going to split the section over multiple videos. So we're going to look at identifying polynomial functions, recognizing characteristics of graphs of polynomial functions, determining end behavior, using factoring to find zeros of polynomial functions, identifying zeros and their multiplicities, use the intermediate value theorem, understand the relationship between degree and turning points, and graph polynomial functions. So we've looked at graphing quadratics, what happens when we had that x squared function. Now we're going to get into looking at what happens when we get to another degree, a third degree, fourth degree, fifth degree, etc. So let's talk about the definition of a polynomial function. It says let n be the non-negative integer and let a sub n minus 1, all the way down to a sub 2, a1, a0 be real numbers with a sub n not equal to 0. Otherwise, that leading coefficient, if that was a 0, then that wouldn't be the highest power that you have. Kind of looked at this a little bit already. It says the function defined by f of x is equal to the a sub n of x to the nth plus a sub 1 less on your n value, all the way down to you get to the a sub 0, that final constant value. It says that whole thing is called a polynomial function of degree n. The leading number, a sub n, is the coefficient of the variable to the highest power, called the leading coefficient. We kind of already talked about that so far this year. So it says graphs of polynomial functions. It says that polynomial functions of degree 2 or higher have graphs that are, the first characteristic is that they are smooth. The graphs contain only rounded curves with no sharp corners. Like an absolute value has a V shape, that's a sharp corner. All of our polynomial functions are going to have smooth curves. The next thing says that they are continuous. It says the graphs have no breaks and can be drawn without lifting your pencil from the rectangular coordinate system. Continuous meaning as you start graphing, you are never going to pick up your pencil and jump spots. Talks about the end behavior of polynomial functions. It says the end behavior of the graph of a function to the far left or the far right is called its end behavior. Kind of what you don't see on the graph, right? It kind of goes off to the infinities. They're either going to go all the way positive infinities or negative infinities or one of each. It says, although the graph of a polynomial function may have intervals where it increases or decreases, the graph will eventually rise or fall without bound as it moves far to the left or far to the right. The signs of the leading coefficient, a sub n, and the degree of the polynomial function reveal its end behavior. So we are going to pay attention to the sign, and we are going to pay attention to the degree to kind of tell us what's happening with those end behaviors. So the leading coefficient test, it says as x increases or decreases without bound, the graph of the polynomial function, that really ugly thing, eventually rises or falls. In particular, the sign of the leading coefficient a sub n and the degree n of the polynomial function reveal that end behavior. So as I said before, the main things that we're focusing on, we're going to look at the sign. Is it a positive or is it negative? And then the degree. And pretty much what we're going to do is we're going to be checking to see, is it even or is it odd? So the leading coefficient test, let's see what it tells us. It says for odd and then for even. So we have two different pieces. We have if n is odd. That means that you're looking at a third degree, fifth degree, seventh degree, ninth degree, etc. It says if the leading coefficient is positive, the graph falls to the left and it rises to the right. So that means we're falling to the left and we're rising to the right. That is if A is positive. A is positive. It says odd degree, positive leading coefficient. And then it says if the leading coefficient is negative, right, that's what a sub n less than 0, that's going to be a negative a value. It says the graph rises to the left and it falls to the right. It says if we have an even function, they're going to go in the same direction. So it says that the leading coefficient is positive, right? If a sub n is positive, it's good. They're both going to the positive. If the leading coefficient is negative, a sub n is less than 0, we have a negative, that means that they are both going to fall. I think the even kind of makes the most sense. If it's positive, they're both going up. If it's negative, they're both going down. The one that gets a little tricky is the odd. And kind of the easiest way for me to kind of explain odd is if you go to a regular linear function, right? If you think about linear functions, if you have a regular normal graph, a linear function, right? One of them's going down and one of them's going up. That's what happens when you had a linear function. One is going down and one is going up. So if A is positive, it's like having a positive slope. You go from the bottom all the way to the top. And then if you have a negative, you're doing the opposite, if that kind of makes sense. So let's look at an example. It says, use the leading coefficient test to determine the end behavior of the graph of f of x is equal to x to the fourth minus 4x squared. Excuse me. It says the graph of the function is what? The degree of the function is what? So we're going to look for that highest power. The degree of the function is 4. And it says which is what? Is that even or is that odd? Well, that's even. If we have even degree functions, it says they have graphs with the same end behavior, right? If they're even, they're either both up or they're both down. So if we look at the leading coefficient, well, what's the leading coefficient? What number is in front of that x to the fourth? Well, that's just a positive 1, right? It's a 1, which is positive. It says that the graph is going to do what? If it is a positive, are they both going up? Are they rising or are they falling? These are going to rise to the left and to the right. So the graph rises to the left and to the right. So if we were to kind of draw, and this is just going to be a really ugly, rough sketch, because it's not going to be perfect. What it's saying is that we are going to end up with a graph that's going to end up rising in some way, shape, or form. And actually what happens in between here, and again, this is, as I said, just a rough sketch. This is going to come down, go up, come down, and go back up. A fourth power almost looks, in a sense, like a W shape. It's almost like a double parabola, right? A parabola x squared. If you were to double that, you have x to the fourth. It kind of makes this funny looking W shape. As I said, it's not perfect. It's just a rough sketch, but that's pretty much what's happening. The idea is to be able to figure out that the end behavior, both of these are going to end up rising. That's that leading coefficient test. So let's talk about zeros of polynomial functions. And this is where we get into some vocabulary that you're going to see often. It says if f is a polynomial function, then the values of x for which f of x is equal to 0 are called the zeros of f. If you remember any of our regular quadratics, when we are solving to figure out what zeros are, we're looking for these intercepts here, right? So these pieces here are what are called zeros. It says these values of x are the roots, so they're also called roots, or the solutions, they're called solutions, of the polynomial equation f of x is equal to 0. It says each real root of the polynomial equation appears as an x-intercept of the graph of the polynomial function. So in general, what we're looking at for zeros of polynomial functions is anywhere it's crossing the x-axis. They're going to call them zeros, roots, or solutions. All three of those words are interchangeable. Let's try an example. Find the zeros of the polynomial function. We have f of x is equal to x to the third plus a 2x squared minus 4x minus 8. Excuse me. So we find the zeros of f by setting f of x equal to 0 and solving the resulting equation. So we're going to take in place of f of x, we're going to turn that into 0, and we have a polynomial function, which means that we're going to do some factoring. Since we have 4 terms, we could factor by grouping. So if we group these first 2 pieces together, we group the second 2 pieces together, let's see what we have in common. So x to the third plus 2x squared, we'd factor out an x squared, which would leave us with an x plus 2. If we have a minus 4x and a minus 8, what's in common would be a minus 4, which would leave us with what would be a positive x and then a positive 2. What's in common here? We have an x plus 2 in common. And then we have an x squared minus 4 left over. And if we were to break that down further, that is a special case. X squared minus 4 means that we have an x plus 2 and an x minus 2. And if we were to continue solving this down, that means that we'd have x plus 2 is equal to 0, which means x is equal to negative 2. We would have this x plus 2 is equal to 0, which means x is equal to negative 2. And this x minus 2 equals 0 means that x is going to equal a positive 2. So we ended up finding our 3 solutions, but 2 of them make the same exact value. We have an x equals negative 2. We see that twice. Maybe you forgot that this was a special case, and when you went to solve that down, that x squared minus 4, you could also set that equal to 0 from that point. Add the 4 over, so x squared is equal to 4. But then when you take the square root, remember you have x would equal positive or negative 2. So just in case you forget that that's a special case, it could still be solved down for x from that step. So if we were to continue on with it, right, we found all of our zeros. We found technically what would have looked like 3 zeros, but kind of makes 2 zeros because 2 of them are the same value. So the zeros of f are, we ended up with a negative 2 and a positive 2. It says a graph of f shows that each 0 is an x-intercept, and then that means that the graph is going to pass through, well, what would be those ordered pairs? Well, if I have an x-intercept of negative 2, it's going to go through negative 2, 0, and it's going to go through positive 2, 0. Excuse me. That means I'm going to have a negative 2, 0, and I'm going to have a positive 2, 0. Now, if I go about graphing this function, we said if we look at that highest power, third degree, and we look at the leading coefficient, what is happening with this graph? Well, a third power means that we're going to have one up and one down. So it's either going to be down like this and up like that, or it would have been up and then down. Well, if I look at that leading coefficient, that is a positive value, which means that we're going to start with the basic concept that one of them is going to, from the left-hand side, go down. So this is going to somehow go down to the left, and it's going to go up to the right. And so what ends up happening in here, and again, we're just going to do a rough sketch. As we continue on, we will get a little bit more detailed with all the little pieces. So this is still going to be a rough sketch. What's going to happen here is that this has to, in some way, shape, or form, hit this intercept at negative 2. And it's going to hit that positive 2, but then it's going to have to do something down here that would kind of loop it back together to keep that continuous smooth curve. So again, this is a rough sketch. This is actually not drawn accurately yet. We are going to build on these sketches. So the last piece we're going to talk about is multiplicities and x-intercepts. It says if r is a 0 of even multiplicity, then the graph touches the x-axis and turns around at that value r. Even multiplicity, meaning if I have 2, 4, 6, 8, etc., if I end up with multiple of those x-intercepts, then we're going to touch the x-axis. Now, if I go back up here, remember what we said about this negative 2. How many of those did we have? We ended up with 2 answers that gave us negative 2. And what happened at that negative 2? Do you see how that graph goes up and it touches and it turns back around? That's what they're talking about here with that multiplicity. So if it has an even multiplicity, it's going to touch the x-axis and turn back around. Then it continues and says if r is a 0 of odd multiplicity means we have 1 of them, 3 of them, 5 of them, 7 of them, etc. It says then the graph crosses the x-axis. Now again, if I go back up here and take a look, we said that x equals 2. We had one of those pieces. What happened at the positive 2? It went through. So if you have an even multiplicity, it's going to touch and turn around. If you have odd multiplicity, it's going to go through that intercept, right? So it says that it crosses that x-axis at r. It says regardless of whether the multiplicity of a 0 is even or odd, graphs tend to flatten out near the zeros with multiplicity greater than 1. So they kind of still, they go up, they flatten out, and they kind of turn around. So flattening out, that's what it means by that.